Natural absolutely continuous and mutually singular measures. Abstract, a linear space can be identified as an integer measure either finite or infinite. Its respective subspaces can be either finite or infinite depending on the dimension of the linear space. An arbitrary subspace will have a mutually singular subspace in the linear space such that the sum of the integer measures of the direct sum of these subspaces will be the integer measure of the linear space. Is a linear space of infinite integer measure. Is a linear space of zero measure. So, every subspace of a linear space can be appropriately suited to the integer measure. A linear operator from a linear space into itself can also be suited with an integer measure that is the integer measure of its range space. The range and null spaces of the linear operator are subspaces of a linear space. It can be taken to task the dimension theorem. It allows the absolute continuous and mutually singular measures partition over the given integer measure that naturally holds for every linear space and every linear operator. 0,1c. The basic linear algebra topics of linear space, subspace, linear transformation, range space, null space, and their dimensions are considered. Usually the linear operator is defined from a linear space into another such that both are defined over the same field. In the present discussion, the linear space can be finite or infinite dimensional and the linear operators are considered on a subspace into itself. The subspace can either be finite or infinite dimensional. Definition 2.2, if is a linear operator with the null space, and B are the bases of Nk respectively, such that the vectors of R spanned by the basis vectors of, then we say is absolutely continuous with respect to and is denoted by K. Definition 2.3, a property is said to hold almost everywhere, i.e., if the set of points where it fails to hold is a set of integer measure 0. This type of working can be done on an arbitrary linear space and a linear operator. Keeping such an idea in view, it can be proceeded as follows. The motive of signed measure is utilized to establish the absolutely continuity and mutual singularity of the measures upon the linear spaces. Chapter 3. Theorem, there exists a natural decomposition on a linear space V, f, of the integer measure such that for some integer measure over V, f, satisfying almost everywhere. Proof, if V, f, is a linear space, then there can be infinitely many linear transformations possible on V, f, satisfying the dimension theorem. That is, if is a linear operator, then 3.1, tvf. Dim rt and tvf plus equals. Remember that R, T, and N, T, are the subspaces of V, F, and the dimension of a linear space is termed as the integer measure of the linear space nothing but the number of vectors in the basis of V, F. The vectors in the basis of the N, T, are linearly independent of that of R, T, and vice versa that satisfies the dimension theorem. Therefore, for every, dim nt rt. Since end, 0 dim ntt equals 1 dim rtt equals. These things satisfy the said statement. In other words such that n01, equals plus. Further, for almost all subspaces W of V, F, WW equals. Hence the proof.